Hello everyone. Today in this recording, I'm planning to solve the homework problems to give you a review of the exam 3 that is going to be happening on April 13th, 2023. And I have the lecture notes open in front of me, and I will make sure to tell you which page to look at whenever you want to find the equations. Okay, let's start with the problem number 1. This problem is, I would say, the hardest problem of the bunch. So you want to make sure that you have for your full attention here. We are told to consider the case where the span-wise circulation distribution for a wing is parabolic. If the total lift generation generated by the wing with the parabolic circulation distribution is to be equal to the total lift generated by a wing with an elliptic distribution. So the parabolic, let's call it L of parabolic, L of P, is going to be equal to L of elliptical. And we already know that elliptical is going to give us the best or the lowest induced drag. We are asked, if this is the case, what is the relationship between gamma naught values for the two? So gamma naught of parabolic, what is the relationship between the two? Gamma naught of elliptic. And what is the relationship between the induced downwash velocities? And if you recall, we use actually W. So W of parabolic. What is the relationship between the W of parabolic and W of elliptic? At the plane of symmetry, so at y0 or y1 equals to 0. So our goal is to find this and this based on the fact that the lift for these two wings for a parabolic distribution and elliptic distribution is going to be equal. Okay. A couple of quick notes, and they are giving us the parabolic distribution as gamma of y equals to gamma naught 1 minus y squared divided by s squared. One quick note here that you have to make sure that you understand is that, let's say this is your wing. And these are two different wings. One has elliptical lift distribution, one has parabolic. So two different wings. For the first wing, let's call this elliptical wing, which is the wing used in the book. They put the symmetry plane. This is the top view of the wing. They put the symmetry plane in the middle, right? And they tell you that you go to y/2 to negative y/2, right? That's why your distribution of circulation looks a little different from the one you have here. So for an elliptical distribution, I'm going to say gamma of elliptical, and y, we have gamma naught multiplied by square root of 1 minus 2y divided by b squared. So this is b over 2, negative b over 2. I'm very sorry. Okay, so the assumption here is that the whole span length is b. From the center of the coordinate system, you're going to have b over 2 in this direction, the positive direction, and negative b over 2 in the negative direction, right? But the assumption they have made here is a little different. They have assumed that your span is 2s, and here you have, at the positive direction, you have positive s and negative s. So we either have to change this parabolic formula to fit the one that our book uses, or we have to change the one that our book uses to fit the parabolic formula that is given to us. I'm going to follow the book, so I'm just going to rewrite this equation for the parabolic circulation as gamma naught. The only thing I really need to do is to replace s with b over 2. Gamma naught 1 minus 2y over b squared. This is actually the starting point. You just have to make sure that your parameters, the things that you are naming and everything are consistent, right? That's the first thing. We have the circulation for parabolic, we have the circulation for elliptical, and we are told the lift for these two have to be equal. How did we calculate lift in these cases? We have the Kutta-Joukowski theorem that told us, and these are all from, this is from page 50, this is from chapter 2 or 3, but it's also, we are reminded of this in page 50 as well. We said the lift per unit span, which is a function of y. The idea is lift per unit span here is different from here, different from here, different from here, because of the downwash, is a function of your free stream density, free stream velocity, v infinity, and gamma of y. But we are told the lift, total lift, not lift per unit span, is equal. So we have to find the lift, which we can find by just taking the integral of circulation from 0, or I'm sorry, from negative b over 2, from here to here, to positive b over 2. Circulation of y dy, and this will give us the total lift. Right? We have already calculated the lift. This is in page 50 again for elliptical. You don't need to do the integration here. For the elliptical, we know that lift is rho infinity, v infinity, gamma naught, b over 4 multiplied by pi. This is something that we have already calculated. But for the parabolic one, we need to take the integral. So lift of the parabolic is rho infinity, v infinity, integral from negative b over 2 to positive b over 2, and this is gamma naught of elliptical, gamma naught of parabolic, 1 minus 2y divided by b squared dy. And the integral of this parabolic lift is going to be rho infinity, v infinity. This is also a constant. We think you can take it out of the integral. And the integral of the rest of it is integral of y minus 2/3 of y cubed divided by b squared. If you have a problem understanding this integral from negative b over 2 to b over 2. If you have a problem understanding this integral, please make sure to come by my office or send me an email or whatever, but this is a polynomial integral. Okay, so we just have to plug in the values that we want, and we should have a solution. If you plug in the values, this is a solution you are going to get to. Rho infinity, v infinity, gamma naught, and parabolic. B over 2 this is 3b over 2. I'm sorry, 2b over 3. Just plug in the numbers and it should give you the values multiplied by pi. Oh, there is no pi here. Yes, that was my mistake. Sorry, so we have this, and we have to set this, the second one, equal to the first one. So L of E equals to L of P, which means that rho infinity, v infinity, gamma naught, and elliptical, b over 4 pi is equals to rho infinity, v infinity, gamma naught, and parabolic 2b over 3. Okay, so all of these are constant, they cancel out, and also b cancels out, and we have the relationship between the elliptic gamma naught and the parabolic one, which is 8 pi over 3. And this was the question, this was the goal of the first part of this problem. So that's 8 over 3 pi. Yeah. The second part of the problem is asking us to actually compare or set the two, calculate the two downwashes and find the relationship between them. So essentially, we want to take the ratio between the two downwashes. If you look at page 51 or page 50, it's page 50 again. Yeah. If you look at page 50 of the lecture notes again, we have already calculated the downwash for the elliptical one at the symmetry plane, which is negative gamma naught of elliptical divided by 2b. Okay, but we need to be able to find a downwash for the non-elliptical bit, for the parabolic bit, and we didn't have an integral equation for this, and you can find that integral equation in page 40. So from page 40, we can see that W, this is for parabolic of y naught, is 1 divided by 4 pi, negative 1 divided by 4 pi, integral of negative b over 2 to positive b over 2, d gamma dy divided by y naught minus y. And we said we are looking at the symmetry plane. So y naught is 0, which means this is page 40, guys. I'm sorry. Which means that the parabolic induced velocity is going to be at 0, is going to be equal to 1 negative 1 over 4 pi integral of negative b over 2 positive b over 2. And we have to look at this here, the parabolic circulation. We are interested in calculating the derivative of circulation with respect to y, which is going to give us gamma naught and parabolic multiplied by negative 4y divided by b. Yes. So you just have to plug this in or substitute in for the derivative in the equation, in our integral. We have negative 4 gamma naught and parabolic divided by b squared. I'm sorry, I forgot the squared here, because there's a square, there's a power 2 here, the denominator goes to as well, and this is divided by negative y, all of this dy. I did forget about the y here. So the two y's here cancel out. We will end up taking the integral of negative b over 2, 4 gamma naught and parabolic divided by b squared dy. All of this is a constant, and the solution to this integral is going to be just y, because that's the integral of a constant. So the two 4's here cancel out. We're going to have negative gamma naught and p divided by b squared divided by pi from multiplied by y from negative b over 2 to positive b over 2, which is going to give us negative 2 gamma and parabolic divided by pi b. And this will be your induced velocity for the parabolic case. We have the induced velocity for the elliptical case, and we also have the relationship between the two gammas. So I'm just gonna write everything as a function of gamma naught and e, essentially the elliptical thing. Gamma naught or gamma naught and p. So just going to substitute this for 8 over 3 pi gamma naught and p, which is going to give you the induced velocity as negative 8 over 6 pi b gamma naught and p. Yep. You just have to compare these two values together. On one side, for gamma and e, we have negative 8 over 6 pi gamma naught and p divided by b, right? And on the other side, for the parabolic one, we have negative 2 gamma naught and p divided by pi b. So if you divide these two, what you're gonna get is the induced velocity of the elliptical divided by the induced velocity of the parabolic is going to be equal to 6 over 4. This is the relationship between the two. You can simplify this to 3 over 2 as well. Okay, so that's the solution to problem number 1. And this is the hardest problem in the homeworks. Let's go to problem number 2. Problem number 2, we are told that the measured lift slope for NACA 23012 airfoil is negative 108. So we are told that this is a lift slope for an airfoil, right? If you go to the lecture notes in, I guess this is page 64. Yes, page 64. Page 64. You'll see that we have two CL versus alpha curves, one for infinite wing and one for finite wing. Since we are talking about an airfoil, whatever value it's given to you for that airfoil is essentially for that infinite wing. So the lift slope here is A naught. So A naught for us is 0.1081. This is per decrease. And we are also told that alpha at 0 lift, angle of attack at 0 lift, is negative 1.30. You just have to keep in mind that this value doesn't change for the finite and infinite wing, because we are talking about the 0 lift case. When you have 0 lift, none of it goes to induced velocity, right? Because induced drag, or induced velocity for that matter, which essentially means that at 0 lift, your angle of attack is not going to change. Let me write this down. At 0 lift, there is no induced drag. This essentially means that the pressure on top and bottom are already equal. There won't be any downwash happening because of pressure difference. Okay, what else? We are also told that to consider finite wing using this airfoil with an aspect ratio of 8 and a taper ratio of 0.8. We are going to assume that sigma is equals to tau for this, which essentially means that we are going to talk a little more about this, because we need to go back to the book and look at one of the tables. Let me open the book in front of me, just 1 second, and I will tell you which table to go to actually have this information. And keep in mind, this is an open book problem, so you should be able to, you must have the tables and everything else with you, because the idea is you are going to bring the book with you. Okay, so if you go to the book, what this essentially means, we have talked about delta, we have talked about tau, and what they mean for each part of the, what they mean for us. We do have this table that is going to talk about delta, the values of delta and taper ratio. This is figure 5.20, page 452 of the book. But we do have this in the lecture notes as well. I just have to find the lecture notes, a specific lecture note page. Just give me 1 second. I can't find it right now. I found it. Yep, this is page 59 of the lecture notes. Whenever you are told that delta is equals to tau, is that you have to go to this figure, to this figure 520 that is in the lecture notes and also in the lecture notes, and you have to read delta. This is this type of plot for this different aspect ratios. We have aspect ratio, our aspect ratio is 8, so you have to look at that specific line, and our taper ratio is 0.8, which falls somewhere here. If you look at this plot for 0.8 and aspect ratio of 8, we have roughly delta of 0.06. I would say 0.06. I'm not sure what is the value we are using in our solutions to this problem. 0.05. I think in the solution we are using 0.05, but we can use 0.06 or 0.05. You just have to be able to read the table. Okay. So, what does this mean? It means that our efficiency factor, which is 1 over 1 plus tau, or 1 over 1 plus delta, is equals to 1 over 1 plus 0.05 or 0.06. I'm just going to use 0.06 for a second, but I have to do the calculations. 1 plus 0.06. So we have to divide 1 by 1.006 or 06, I'm sorry. This is going to give us a value of 0.94. This is very close to elliptical wing. So we have our E, we have our A naught, we have alpha at L equals to 0. We just have to go back and find the equation, find the appropriate equation that was discussed in page 64. But let's actually read through the problem. Okay. We are told to calculate the lift and induced drag coefficients for this wing with a geometric angle of attack of, at the geometric angle of attack of 7 degrees. So the first thing we need to find is the lift slope for the actual wing. What was the equation we had for it? It was in page 64. It is A naught divided by 1 plus A naught divided by pi EAR. This is also equal to, we don't need to calculate the E separately, 1 plus A naught divided by pi AR multiplied 1 plus tau. If you plug in the numbers here, for the lift slope, you're going to find 0.108. You see the lift slope is not very different, up to 3 digits, decimal digits, which means that the induced angle of attack, induced drag shouldn't be that dominant, should be very, very, very small. So let's find the angle of attack. How do we find the angle of attack? We know that lift coefficient is equals to A, which is your lift slope, multiplied by alpha minus alpha at lift equals to 0. We have everything. Negative 1.18 multiplied by 7, which is our degrees, plus or minus, I'm sorry, minus 1.0 or 1.3. This is equals to 0.897. And how do we calculate the induced drag? This is also something you can find from page 51, this equation. We said the induced drag coefficient is equals to lift coefficient to the power 2 divided by pi EAR. Plug in all of the numbers, we have everything. You're going to get 0.034, which is along the lines that we guessed. It has to be a very, very small drag coefficient. Our drag coefficients are usually in the first decimal point. So we have 0.1, 0.2 is a very good drag coefficient, 0.3, 0.4, 0.5 in that range. So in 0.0 something in the hundreds is a very, very small drag coefficient. Let's go to the next problem. We are told that we have a Piper Cherokee, which is a light single-engine general aviation aircraft, has a wing area of 150 square feet. So our area, usually actually use S for area of the wing, as 150 square feet, and a wingspan of 32 feet. Its maximum gross weight is 2,450 pounds. So weight is 2,450 pounds. The wing uses a NACA 65415 airfoil, which has a lift slope of, so A naught is 0.133 per degrees, and a zero lift angle of attack of negative 3 degrees. We are going to assume tau is 0.12 if the airplane is cruising at an altitude of 120 miles per hour at the standard sea level. At its maximum gross weight, and is in a straight level. Is in a straight level flight. Calculate the geometric angle of attack of the wing. So alpha is the question, the final geometric angle of attack. What is the first thing we need to find? In our equations, we have an aspect ratio. So we have to find an aspect ratio, which is b squared divided by s. So 32 to the power 2 divided by 170, which is going to give you an aspect ratio of 6. Okay, that's the first thing. We always have to find the aspect ratio when it comes to wings. But then we have to go back to this last part of it. We are told that the airplane is cruising at this 120 miles per hour at the standard sea level at its maximum gross weight and is in a straight level flight. So cruising straight level flight. What does this tell you? It tells you that your lift is equals to weight. If lift was higher than weight, you would have pitched up. If it was smaller, you would have lost elevation, lost altitude. So we already have our lift, which is 2,450 pounds. Okay. What else do we need to know? We need to know what is the density of air at the standard sea level, and also what is the viscosity of air at the standard sea level, and all of the uh, different air parameters, or the pressure of air, right? And we are all told this here. We don't really need to go to the standard sea level tables and find these. You're all told what these are. So what can we do here? We can actually find, for this specific case, we can find CL as lift divided by 1/2 rho infinity V infinity squared multiplied by the area. So for lift, we have 2,450 pounds, 1/2. For density, we have 0.002377 slugs per cubic feet multiplied by our velocity, which is in miles per hour. So we have to actually convert this miles per hour to feet per second, right? Because that is the standard a standard velocity in the British system, is in the imperial system. 1 miles per hour is equals to 1.4, or we can do 1.46 feet per second. You just have to be very mindful of the units. You have to make sure that you have the units correctly, right? So if you want to make that transition, how many miles per hour are we cruising at? It's 120, right? Yes, 120 miles per hour, which means that we are going to have roughly 170 feet per second, right? 176 exactly, actually. I have to do these calculations right now because my solution is in SI units. We have converted everything in SI in my solution. So for your CL, what are we gonna have? We have 176 and then 170 square feet for your area. If you do the calculations for your lift coefficient, you are going to have 0.4 roughly. Okay. What we are asked to find the angle of attack. How can we find the angle of attack? So our CL is equals to A multiplied by our angle of attack minus the angle of attack at lift 0. This is a geometric angle of attack, and this is actually can be found, all of this can be found in let me find the page number. It is again page 64, but this is something you probably most probably have seen most probably have seen before. So our lift coefficient here is going to be equal to A naught or either A, which is your lift slope for the infinite wing. I'm sorry, for finite wing. And this is your geometric angle of attack. Or you can actually find it using A naught and find the effective alpha minus alpha L equals to 0. And then from this, we can say effective alpha is equals to geometric alpha minus induced angle of attack. But in order to use this, we have to find the induced angle of attack. So this everything is going to be a little more difficult. So let's actually go find the lift slope. Okay, let's go find the, sorry for the notification sounds. Let's go find the lift slope, and then we can plug everything here. We should be fine. How do we find the lift slope? From the lift slope equation. What was the lift slope equation? Again, page 64. We actually have done this once before. It is A naught divided by 1 plus A naught divided by pi E AR, or we are here, we are given tau. So I'm just going to use that other equation. If you plug in all of the numbers which we have for A, you are going to find 0.13. Okay, so CL is going to be equal to 0.13 multiplied by alpha multiplied by alpha minus alpha at L equals to 0. This is -3. This is 0.4. So you can easily find your geometric angle of attack to be 10 degrees. Okay. So, what is the next step? The next step here is to find the drag. Or are we told to find the drag? I don't think so. No, we just had to find this. I'm looking at my solution here. My solution seems to have some sort of a problem. I'll make sure this is fixed before the exam, but just follow this and you should be fine. Okay, problem number 4. For problem number 4, this is a long problem, but most of it is just a hint for us. We're told to consider Supermarine Spitfire. Its maximum velocity is 262 miles per hour at an altitude of 18,500 feet. Its weight is 5,820 feet. Wing area is 242 square feet. Wingspan is 36.1. It is powered by a supercharged Merlin engine, which produces 1,050 horsepower at 18,000 feet. You want to calculate the induced drag coefficient of the Spitfire at the flight condition of maximum velocity. So our velocity is 362 miles per hour. So again, we are dealing with miles per hour. We have to multiply this. We have to convert this to feet per second. That is going to be your first step. So let's do the conversion. 362. We are going to have V max is going to be equal to 530.993 feet per second. That is our V max. And for part B, we are also told to find the percentage of the total drag that is induced drag. Okay, how can we actually go ahead and find this? The first thing you want to do is to find the lift coefficient. So let's do the part A first. Lift coefficient, we are cruising again. So lift coefficient, which is equal to 1/2 rho V squared S, it's going to be equal to W. Because at cruising speeds, at a straight level flight, your lift has to be equal to your weight. If you plug in the numbers, your weight is 5,820, and we have 1/2. Well, what is the density? Again, a standard atmosphere. You have to go to the standard atmosphere tables, look up all of this at a specific altitude, but it is going to be given to you for all of the everything you need. So we have the density as 1.3329 10 to the -3 slugs per cubic feet multiplied by 530.933 multiplied, this is squared, multiplied by your span area, which is 242 square feet. This calculation is going to give you 0.128 for the lift coefficient. Okay. Our goal here is to find the induced drag coefficient. we have CDI is equals to CR squared divided by pi EAR. Let's see if we are given any information about E. We are told that it's a supermarine Spitfire. And if you recall, we actually talked about this in class. A Spitfire has an elliptical wing, which means its E is actually 1, right? Aspect ratio, B squared divided by S. And what is B squared? For B, we have 36.1 feet. You plug in the number here. Squared divided by 242, which means that your aspect ratio is going to be equal to 5 times 0.39. And we have found the lift before. So your induced drag coefficient is going to be equal to 9.67 times 10 to the negative 4. This is a very, very small induced drag. But how can we actually find out how much of this is going to your how much of the drag is actually coming from your induced drag? It should be a small percentage, right? Because it's 10 to the negative 4. It's a very, very small percentage. Let's actually see what we can find here. So how can we find the drag? We are given the engine power. The engine power that is given to us is 1050 horsepower. Okay, and that's all we are given. But we are also told that the maximum velocity we can fly at is already achieved. And we are flying at this velocity, cruise conditions. So this is a straight level flight, which means that the flight is unaccelerated. Let's look at this plane. Very badly drawn plane. We have lift, weight, drag, thrust. And thrust comes from this power, the engine, right? If you have an unaccelerated flight in any direction, what does this mean? That it means that there is no force, total force in that direction, which means that there is perfect force balance in every direction, which means that thrust has to be equal to drag. So we can actually find the drag by finding the thrust. But what is the relationship between thrust and power? Power is joules per second or watts. What is thrust? Newtons, right? Units in SI, right? On the other hand, joules itself is newtons multiplied by meters, right? Energy is equals to force multiplied by the distance, right? The force you actually have to have to be able to move something at a specified distance, right? Which essentially means that in newtons is joules per meters. So what is the relationship between joules per meters? Or how can we convert joules per meters, which is our thrust, to power and vice versa? What happens if I multiply this by or divide this by meters per second? I'm gonna get joules per meters, right? This is dimensional analysis. So this should tell you that thrust is actually equal to power. This is power. This is thrust divided by velocity to infinity. Here you go. Which means that drag in our case is equals to power divided by v infinity. But the units of power for us is actually in horsepower. Well, what is the units of power in the imperial system? Let's actually take a look at this as well. What is the units of energy in imperial system? Energy is power per time. Power is energy per time. The units of energy, again, it is force multiplied by the distance. So it is foot, which is your distance, pound, or pound foot. And if you divide it by time, you are going to have the units for power. So we need to find what the conversion rate between the horsepower and pound foot per second, which you can actually find with a very simple Google search. Every 1 horsepower is equal to 550 foot-pound per second. And what is the horsepower that is available to us? Is 1,500. So 1,50 horsepower is going to be 550 multiplied by 1,050 foot-pound per second. But if you read through the hint that is given to you, you are going to see that this is the power provided by the engines. It is not necessarily the power that is delivered to the aircraft. I mean, there are some losses in the shaft and the gearboxes and all of those things, and we don't really consider those losses. But the problem is asking us to assume that those losses is going to cut our energy by 10%, meaning that our efficiency is actually 90% or 0.9. So whatever value I have here, I have to multiply by 0.9. And that will give me a drag of, and this is going to give us power, and then we have to divide it by velocity, which is 530 feet per second, right? Which means that your drag, let me actually plug this in, is going to be equal to power divided by velocity, 550 multiplied by 1050 multiplied by 0.9 divided by 530.933, which is going to give you a value of, I'm looking at my solution, writing this value, 978.94 pounds. So drag coefficient, total drag coefficient is drag divided by 1/2 rho v infinity squared s, which is going to give us a drag coefficient of 0.0215. And how much of the drag comes from total drag? This is the total drag. Total drag coefficient. How much of it comes from the induced drag? We just have to divide the induced drag by the total drag, and that will give us 0.0449, which is equal to 4.49%. So that is it for the homework. There are only 4 problems. Hopefully you will be ready for the exam by Thursday, but if not, let me know. I will try to incorporate some explanatory problems. Again, the homework is open. Exam 3 is open everything. And that everything is everything, including the solutions to the homework problems. And undergraduate, I'm not sure about this policy. Essentially, we can discuss this later in class today. But the other policy that we have is that you will get 1 question from compressible and shock waves, fluid flow parts. And that one question is going to be worth 15 points. It doesn't mean that it is an easy question though. And you have to choose either of this. There is no partial here. You either solve this or you solve the other problem, the regular exam problems. And tomorrow, or today, I'm sorry, later today, in the class, we are going to go over this topic a little bit. And this is based on the request you guys had in class on Thursday. Okay? See you later today. That's it for today. And have a good day. I'm sorry.